This video is electrostatics and vector E fields. So let's start with a vector E field. I've got to have a charged object to begin with, and this is going to provide the structure in space to exert a force on another charged object. So what I'm going to do is I'm going to populate the screen with the field of vectors, where the length is going to represent the magnitude and direction of the electric field. So let's start with the magnitude electric field. I have a relationship already defined for that. E is equal to 1 divided by 4 pi epsilon naught, which is a constant, times Q over R squared. You might also know this as E is equal to KQ over R squared. So what this means is that the electric field is inversely proportional to the square of the distance away. So I got this inverse squared relationship between E field strength and the distance away. So to draw a vector field, I'm going to pick a point in space, and I'm going to put this imaginary massless point charge out there. I know it sounds kind of odd, but that's how we do it. So here I have this positive test charge, and when it's out there, it's going to be some distance away from the charge. I'll call that distance x. So if the charge is positive and the point charge, the test charge, is positive, they're going to be repelled from each other. So it's going to move upwards, and that's going to be the direction of the electric field. So to make a vector, I need magnitude and direction, and there's the direction. It's just a logic problem of which way would it travel. Now I've got to figure out the magnitude. So the magnitude is E is equal to 1 over 4 pi epsilon naught Q over R squared. So I can calculate that magnitude and give it a number. Or in this case, what I'm going to do is I'm going to draw that, and I'm just going to use my inverse squared relationship to figure out what else is going to happen here. So I'm going to draw that some number of pixels long. Let's say 144 pixels long. So that's the size of it. And I'm going to make a field of them. So I'm going to pick a bunch of test charges, all a distance x away, and they're all going to be repelled. And so there's the beginning of my vector field. Now what happens if I move my point charge a little bit farther away? Let's say 2x. So if I move it twice as far away, it's an inverse squared relationship. So the inverse of 2 is a half, squared is a fourth. So the magnitude electric field at this point 2x in space is 1/4 of the original. So I'm going to draw my arrow 1/4 as long. So if the first arrow was 144 pixels, this arrow is going to be 1/4 that, or 36 pixels in length. So it's drawn 1/4 at that point. Now again, it's a field, so I'm going to draw dots all around this charged object and draw their lines to be 1/4 the length of the original one. Okay, let's keep on with this trend and see what happens when it's 3 times farther away. So the original vector field was at a distance of x. This is now 3 times x. So it's 3 times x, so that's going to be the inverse of 3, that's 1/3, squared is 1/9. So electric field is 1/9 of the original. So at this time it's going to be 16 pixels long. The original was 144, 1/9 of 16 pixels long. So now here I am at 3 times the distance and a much shorter vector, but I got to create my vector field, so I'll put a lot more dots at 3x distance around, and I'll draw those vectors. And now I've got a nice vector field, and where the length of the arrow indicates the direction and magnitude of the electric field at the point in space, and the point in space is always the tail of the arrow. So when I'm comparing these two, one of this is 3x, so it's 1/9 as long as my original one that I drew. And I arbitrarily picked the original one to be 144 pixels long. It could have been anything. I just picked it like that because that's the way that my computer did it. Now what would you do if, say, instead of a positive charge, I had a negative charge in the middle? Well, it's the same process. So here are the original points that I had when I ended up with my last talk about the electric field. And if I look at them, if they're positive and the charge in the middle is negative, they'll all be attracted to the negative. So I'll draw my line this time, also 144 pixels, but it's going through the middle, so it's going across the middle. It looks kind of cool. And now it'll be a little bit easier to see what goes on when I draw the next ring. This time it's 2x as far away, inverse squared, so 1/2 is a half, squared is 1/4. So this arrow is 1/4 as long, and my dots are always positive, always positive. So the positive charges are going to be attracted to the negative charge in the middle, so they're going to point to the inside. And now the ones on the outside, they're 3 times as far away, so that's 1/3, it's 1/3, squared is 1/9. So their vector is going to be 1/9 as long, and these imaginary positive charges will be attracted to the negative in the middle. And so that's what the negative vector field would look like.